Hello and welcome to the first of 3 lecture videos covering Chapter 28, Atomic Physics. These 3 lecture videos are going to focus on the slideshow, which is going to cover the material in the chapter, in as much as it is going to cover the historical background of the material, introduce the equations, introduce the key concepts, and ask some concept questions. The equations used in numerical examples will be showcased in the next lecture, which will be, let's see, that would be lecture 26. Okay? And to be clear, this is lecture 25, video 1, covering chapter 28. All right, so the topic is atomic physics. Let's talk about atomic physics. All right, so the first kind of beginning of these ideas is that in Newton's time, okay, so before modern physics, the atom, if it was thought about, was thought to be a tiny, indivisible piece of matter. It was the smallest that matter could become. Matter was built of these atoms, these building blocks, and they were thought to be hard and indestructible spheres. Okay, so this model made a lot of sense for the basis of kinetic theory, which we discussed, which has some complicated results, including the average kinetic energy of an ideal gas, and so on. Right? These are thought of as being a step above historical classical physics, but they were still based on assumptions that date back to Newton's time. Atoms are just little balls, right? Okay. However, new models had to be devised when experiments revealed the electronic nature of the atom. So everything we talked about regarding electricity and magnetism really necessitated the need for a new model, because now we understood that atoms had positive and negative charge, and they had different amounts of positive and negative charge. This led to a theory by J.J. Thomson. So we can think of this as the first of the modern theories of the atom, and this would be in the early 19th century, very early 19th century, that suggested that a model of the atom would best be described as a volume of positive charge, as shown here in the picture, right? So essentially a sphere, an encompassing sphere, kind of a solid mass of positive charge with the electrons suspended within that sphere of positive charge, like the seeds in a watermelon or the raisins in a pudding. Okay, and so that's the idea here. You will sometimes hear it described as the plum pudding model. Okay, so that was the model, we could say, at the turn of the 20th century. However, in 1911, Ernest Rutherford, who was, along with his student, Hans Geiger, whose name is associated with the Geiger counter, which measures nuclear radiation, performed a critical experiment showing that Thomson's model couldn't be correct. In this experiment, a beam of positively charged alpha particles were projected against a thin metal foil. Okay? I know at least in one version of the experiment that would have been a gold foil, so a very large atomic nucleus, as we know. Gold would have been chosen because it's very dense, and maybe there would have been some intuition there, some basic idea that being a dense material, perhaps it was composed of large atoms. We now know that means large nuclei. Most of the alpha particles. Now, remember, alpha particles are well. Let me rephrase that. Let's see, because we've discussed, we haven't discussed versions of radioactive decay. So we haven't really seen the alpha particle, but let's see, have we? No, not in depth. Sorry for just thinking about it. Basically, the alpha particle is an ionized helium atom. It's 2 protons and 2 neutrons. So the important thing from our perspective is it's positively charged, the alpha particle. So definitely when we think about Coulomb forces, think of it as a positive particle. And it's got the mass of about 4 protons. Okay? So these alpha particles, which can be produced through radioactive decay, which is how they would have had access to them through for this experiment. Well, anyway, most of them just passed right through the foil. And we're kind of seeing that here in the picture. They're passing right through the foil, kind of uninterrupted. Okay? So they're not hitting something and bouncing off. However, some of them scattered through very large angles. All right? So some of them bounced off at 90 degrees or even were returned in the direction that they came from. Such large deflections were not expected by Thomson's model. A positively, because if there's just kind of this like positively charged mass that holds the electrons, then either, it's kind of a loose web of positive charge and the alpha particle should be able to pass through it no matter what, or the whole atom should deflect most of the alpha particles because there's this big glob of positive charge with electrons housed within it. But if some of them are, that tells us that the positive charge must be more localized. Okay, so the positive charge in the atom, something we take for granted today, but the positive charge inside the atom must be localized, what we know now to be the nucleus of the atom. Okay, so this was a turn to a revolution in the way we thought about atoms. Okay, so now we are into the Rutherford model of atoms, that they have a center of positive charge. Okay, so Rutherford explained these results by making the assumption that the positive charge in the atom was concentrated in a region called the nucleus. That was small relative to the size of the atom, thus very few deflections. But when there were deflections, they were very, very significant. Rutherford visualized the atom's electrons as orbiting the nucleus, much as planets orbit the sun, okay, as we see in this picture. The alpha particles used in Rutherford's experiment were later identified as the nuclei of helium atoms, as I said. So definitely a net positive charge on the alpha particles, thus their repulsion from the positively charged nucleus. Okay, there were two basic difficulties with Rutherford's planetary model. Okay, so this is where we're going to get into the whole series of questions about how are we going to model the atom. Okay, first, an atom emits certain discrete characteristic frequencies of electromagnetic radiation and no others. The Rutherford model was unable to explain this phenomenon, so we had a complete lack of explanation. So obviously this was not going to be the end-all model. Secondly, the electrons in Rutherford's model undergo a centripetal acceleration because they're going in an orbit, right? That requires a centripetal acceleration, okay? However, according to Maxwell's theory of electromagnetic radiation, an accelerating charge would produce an electromagnetic wave, right? Accelerating charge means change in velocity, means a changing electric field, which produces a changing magnetic field, thus you have an EM wave, okay? But that means that EM wave that is being produced by the centripetal motion of the electrons, well, that would carry away energy. As the electrons radiate energy, the radius of the orbit would steadily decrease and the frequency of revolution would increase. This process would lead to an increasing frequency of emitted radiation, basically a positive feedback loop where the energy, not positive in a positive connotation, but positive where one thing leads to another, which leads to a stronger thing, which leads to a stronger thing. And so in other words, more and more energy would be radiated away, and this electron would quickly crash into the nucleus. Well, either atoms are fundamentally unstable and somehow they're just being regenerated all the time, or we have a serious issue here with this idea of thinking about electrons orbiting the nucleus in the way that the planets orbit the sun. Rutherford's model of the atom gave way to that of Niels Bohr. So we'll talk about the Bohr model next, which explained the characteristic radiation emitted from atoms. Bohr's theory, in turn, was supplanted by quantum mechanics. These two theories are based on studies of atomic spectra, the special pattern in the wavelengths of emitted light that is unique to every different element. Okay? So the idea there is that when we're looking at atoms, the way to tell if our theories are correct is to look at their spectra. Okay? In particular, if we're interested in the electrons of the atom. And in this chapter, we say atom. We're really talking about studying the electrons. And you can think historically there was no way to study the nucleus. The nucleus was truly just a indivisible solid mass at the center. Now we know that the nucleus is composed of nucleons. Those nucleons themselves are composed of quarks. The nucleus can emit energy. The nucleus has energy levels much like electrons and so on. But these ideas were inaccessible in the early 20th century. And I bring that up because we are going to focus on electrons, electron energy levels. But the point being that electrons and their energy levels were a window into the atom, okay? And so all the models are tested by what light is doing, both being absorbed by the atom and then being emitted by the atom, okay? As we go to more sophisticated models, the next one is going to be the Bohr model, okay? As we talk about all these different models, some in more details than others, because we get to the most modern models, we're limited with the mathematical ability that we can discuss them. I want us to consider the lab that I have assigned for next week, because the lab, and that would be, let's see, lab 12? No, lab 11. Quantum mechanics of the, so lab 11 is all about looking at these different models of the atom. And I think it's a great visual tool, a great way to explore those models and make sure you can remember what are the fundamental differences between the models, going from the earliest idea of the Rutherford model up through the Thomson model, or excuse me, Thomson, the Rutherford, onto Bohr, onto the Broglie model, and finally the Schrodinger's model of the atom. All right, so let's move on to these lecture slides. So if we're going to use the light absorbed and emitted, in this case emitted, by atoms, we have to understand the idea of the atomic spectra and why, as I said a moment ago, it is unique to every atom. So suppose an evacuated glass tube is filled with hydrogen or some other gas at low pressure. If voltage is applied between metal electrodes at either end of that tube, then the gas begins to glow. The tube emits light having a color that depends on the gas inside. In fact, that's how a neon sign works. When the emitted light is analyzed with a spectrometer, that could be a diffraction grating or a prism of some sort, you can see discrete bright lines, each having a different wavelength or color. Such a series of spectral lines is called an emission spectrum, right? So here's an example of an emission spectrum for hydrogen, for mercury, and for neon. Because no two elements emit the same spectrum, this phenomenon represents a reliable technique of identifying elements in a gaseous substance. So certainly it can be used to identify elements, so that in itself is wonderful, a wonderful application. But why? Why do different atoms have these characteristic spectrum, okay, or spectra? Well, so you can think then that the spectra were actually discovered before the answer to the question of why came along. So the spectra came first. Scientists recognized the spectra. They recognized that they represented different gases, named gases, but we still didn't quite know why. We assumed it had something to do with the electron level, historically speaking, but what's going on? Why is that? Why are only particular energy levels allowed? Because certainly the idea of an orbit doesn't restrict energy levels. There's nothing restrictive about the different energy levels in this orbital model. So where does the restriction come from? Why is it that hydrogen only can emit a color of green that is that particular wavelength, only has one color in the longer visible wavelength that corresponds to a red? Why is that? Where do these bands come from, these bands of one particular wavelength? Well, in getting there, to answering the why question, we first needed to understand numerically exactly what the bands represent. So we get to something called the spectra, and we'll talk about a couple of these named series of wavelengths. We call them series, and so we're going to have the Balmer series, Rydberg series, and so on. And again, these predate the explanation of where they came from. Okay, so in this figure, we see the emission spectra of hydrogen. It includes 4 prominent lines that occur at wavelengths of about 560, 490, 430, and 410. In 1885, Johann Balmer found, right? So look, we are significantly 15, 20 years before any of this stuff really was explained, but found that the wavelengths, these lines can be described by the simple empirical equation, right? So this is just an observation, right? This isn't derived from anything else. It's saying, oh, look, this works. This must mean something. I'm not sure what it means. Okay, so the idea with this equation is that in the equation, I should say, n is just an integer, okay? It can have values, any integer value of 3, 4, 5, and so on, okay? So it has to be anything larger than 2 in this case, so it can't be 2 or 1. It because we can't get a negative. But any value larger than 2 is completely allowed for our integer value, integer n. Okay. Okay, and for example, the line at about 490 nanometers corresponds to an n of 4, and so on. Okay, the constant in front, r sub h, is called the Rydberg constant. This would be an empirical constant that fits the integers to the particular wavelength of light, all on the scale, the speed visible light, all on the scale of nanometers. So, in addition to the Balmer series of spectral lines, the Lyman series was discovered for hydrogen, which fell into ultraviolet, so invisible but detectable by certain sensors or photographic papers. All right, and the equation that models the spectral lines is called the Rydberg equation. Okay, so the Rydberg equation is this one here. So this one is not specific to Balmer. All right, so this one here is Balmer because Balmer was the first one that was discovered because it corresponded to the wavelengths that were visible. Obviously, the first place that scientists would go. Later, series of colors were discovered that were beyond human vision, and that was the more, robust here Rydberg equation. Okay. So the Balmer series corresponds to a m of 1. Oh, okay. So actually, the m of 2 would be. I thought that was the Balmer series. Let's see. So m of Yeah, okay. M of 1, and for the Passion series, M of 3. Okay. So which one? Hold on. So I want to get my series names right here. I thought the Balmer one was M of 1. Let's see. So we have Lyman, Balmer, and Passion are the particular series. Let's see, do they come? Do we have a name for them? Okay, well, we'll leave it there. But importantly, that you can have, in practice, M is either going to be 1, 2, or 3, and those do correspond to the different series. I'll go ahead and throw that in the next set of notes so you know which name corresponds to which. I think Balmer is M of 2. I think that was the one that corresponds to visible light. M of 1, I think, is the Lyman, and then M of 3 is the Passion series, or Pashan series. Okay? But the names, they just all represent the fact that this was all that was known at the time. So it was a big deal to find one of these sort of trends in physics, because it was just an observation. It was kind of it wasn't like fundamental research. It was like, discovering a new comet or something. It was just oh, look, this is interesting. Okay? But the big question is, where is this coming from? Why do these series exist? So absorption ended up working the same way. So if we were to shine white light, so all of the colors, right? Because again, white light, think black body radiation, is created by molecular, so molecule much bigger than atom, vibrations. And it creates every particular wavelength because electrons are accelerating at every possible combination of rates. And so you have a full width of color. Maybe, there's a peak wavelength at one point, but there's still a probability of all these other wavelengths existing. So if you take that type of light, white light, which comes from black body radiation, it's a good thing to keep track of, right? Then what's going to happen is then that light, if you shine it onto an atom or a gas that is composed of a single type of atom, then only particular colors will be absorbed. And so what we're looking at here is the idea of an absorption pattern. For the same reasons as the emission pattern. And the black bands in the absorption pattern exactly match up with the color bands in the emission pattern. Because you see what's going on here? The atom can absorb the same colors that it can emit, okay? And nothing else. Okay, so here we are, right? We're at a crossroads of physics. We've got an idea that the atom has structure, the electrons are doing something, the nucleus is small and concentrated and composed of positive charge, but what is it the electrons are doing? Because they can't be orbiting in a classical sense because of Maxwell's equations. And they seem, in whatever it is they're doing, if they're not orbiting, they exist at particular levels. It's like they're suspended in space, but they can only be suspended in a particular location. It's like an invisible staircase, but the steps aren't evenly spaced. What is causing this? How do we explain this? Okay, so what happens, what goes on is kind of a lot of intermediate steps, because the pieces to fully explain it did not come right away, but more evidence came, more trends, more patterns were recognized. And that takes us to a model that's still so famous today because of what it led to, not because it really applies to many situations. And that is the Bohr model. And this will conclude this video. I'll talk about the Bohr model and then stop. Now, the Bohr model is interesting. First of all, because as I said, it's a building block for ideas that modern physics does support. Furthermore, it does work very well, coincidentally, for hydrogen, right? It just works well for hydrogen. So you can actually use it as a perfectly, to very small percent error, accurate model for hydrogen. It doesn't work well for heavy elements because it has some fundamental flaws in it, okay? But it turns out because hydrogen is just a single proton being orbited, quote unquote, by a single electron, the Bohr model works well. Okay, so let's get into the Bohr model. So at the beginning of the 20th century, it wasn't understood why atoms of a given element emitted and absorbed only certain wavelengths. I think I made that clear, right? We knew what the wavelengths were, but we didn't know why. We only knew what some of the series were. In 1913, okay, so we're talking, like 30 years after, the first series were recognized by Balmer, Bohr provided an explanation of the spectra of hydrogen that included some features of the currently accepted theory. His model of the hydrogen atom included 4 basic assumptions. So it's kind of an evolution of this Rutherford model. It's kind of this idea, of the Thomson model. It's kind of this idea that there's these orbits, but they're kind of quasi-orbits. How are we going to mathematically explain them? So let's see what the 4 basic assumptions were. Number 1, the electron moves in a circular orbit, okay, around the proton under the influence of the Coulomb force of attraction, okay? The Coulomb force produces the electron's centripetal acceleration, okay? So there we are literally treating it like a classical planet, except instead of gravity holding the system together, it's the Coulomb force holding the system together. 2, only certain electron orbits are stable and allowed, okay? So the orbits are special, they're stable. And because they're stable, the electron can't lose energy and spiral inwards because it's impossible. There's something stopping it. The orbits are like grooves, imaginary grooves, okay? 3, okay? Radiation is emitted by the hydrogen atom when the electron jumps from a more energetic initial state to a less energetic state. The jump can't be visualized or treated classically, okay? So now we're ending the planetary analogy. The frequency of the radiation emitted in the jump is radiated in the change in the atom's energy. Okay, we're going to use H, Planck's constant, the constant that was discovered with blackbody radiation and the quantization of those little those oscillators that were supposedly at the surface of solid absorptive materials. And the frequency of the radiation is independent of the frequency of the electron's orbital motion. Wow. Okay. So because again, we're not letting these electrons that are in an orbit of sorts, right? Because we're still saying that they're in orbit, but we're not letting them emit light like they should according to Maxwell's equations because somehow this orbit is restricted. But we are letting them jump from one orbit to another. But when they jump, they lose energy in a way that, again, has nothing to do with their actual centripetal acceleration. Wow, so we kind of having it both ways with this model, right? We're giving them centripetal acceleration, we're giving them emission of energy, like centripetal acceleration would say based on Maxwell's equations, but we're saying that in fact the emission of energy via photons has nothing to do with Maxwell's equations. Oh, okay. So it's something else. So Bohr needed a new way to explain, first of all, what that energy was in a way that worked, so a mathematical form that matched the evidence, like the Balmer series and the Lyman series and so on. Okay, so that's going to get us to a model. A model that it just has a lot of kind of variables, right? It's going to have a lot of integers for counting different things, and then ends up even being held on to and kind of modified with some ideas from quantum mechanics, and some new numbers and integers really are introduced into the equations. None of them are perfect, actually. Okay, but turns out that, like I said, it works well for hydrogen, and with certain corrections from quantum mechanics, it can work well for a lot of things. Okay, so one thing that we want to say about the Bohr model, and I may say this again, but I want to make this clear now, is that kind of the underlying premise, and it gets a little technical, so we won't get into it too much, but the underlying pretense, the idea that Bohr wanted to present was that it was angular momentum was quantized. Okay, so really that was kind of his incorporation of modern physics, because we are talking 1913 here. Okay, because we knew about quantization of black body radiation, right? We knew about quantization of photons because of the photoelectric effect. So quantization within these quote-unquote orbits, these quasi-orbits of the electron, seemed reasonable. But it couldn't be the energy. The energy just didn't work out. There was no way to quantize the energy. Okay? Turns out that there ended up being energy steps, but it wasn't fundamentally the energy that was quantized. At least Bohr didn't think so. So instead, he based all of his mathematics on the idea of quantizing the angular momentum, which also kind of made sense because Planck's constant has units of angular momentum, joule seconds. And so there was kind of a natural opportunity to quantize that quantity. Okay, so moving on. Okay, so the fourth assumption was finally got there. The fourth assumption was that the circumference of the electron's orbit must contain an integer number of de Broglie wavelengths, as shown in the figure, because of the Broglie wavelength of the electron is given by the equation, right there. Okay, so here we have the de Broglie wavelength of these electrons. The velocity of the electron would be related to the uniform circular motion that it's undergoing in a sort of quasi-classical state. And so this was the idea. This restricted the orbits. Now, this is sometimes presented as kind of a separate model, and indeed the lab does exactly that, and it's totally valid to kind of think of it. There's a lot of kind of series of publications at this point. Of course, this is 20th century science, right? And so, as Bohr continued to research his model, one big addition was the idea of the de Broglie wavelength fitting in within the Bohr model. Okay, and so it lended a certain justification to the Bohr model. It said that essentially what the Bohr model was doing was creating these standing waves, or the electrons were creating standing waves. And of course, the electrons were wave particles after all, so maybe they should have standing waves. Okay? Now, it turns out that that's actually really on the right track. It's just that the wave they have is quite a bit more complicated and quite a bit more three-dimensional than the Bohr model and the de Broglie model suggested. And I think that really makes a lot of sense. And I'm sure that at the time, these scientists recognized that this model had to be an approximation, because they literally were treating it as very two-dimensional. Now, in the sense of solar systems and planets, there actually is a good explanation of how solar systems are formed from many particles that leads them to be mostly two-dimensional entities. All the planets do orbit in almost an orbital plane, and but that's not true of electrons, right? There's no such argument between collisions and an eventual conservation of angular momentum to suggest that electrons should be planar in their orbit, and they're not. They're not planar at all. Okay, all right. Okay, so let's continue on with discussing the Bohr model. Okay, so with these four assumptions, we can calculate the allowed energies and emission wavelengths for the hydrogen atom using the model pictured here, right? So here is our little orbit of an electron. Okay, so in this picture, the electron travels in a circular orbit of radius r with an orbital speed of v. The electrical potential energy of the atom is given by the following equation, right? And this is the equation that would come right out of the Coulomb force, the potential energy of the Coulomb force. We've seen this before. You did a post quiz on this type of potential energy. K is the Coulomb constant, which is just equal to 1 over 4 pi times the emissivity constant. Okay, we've seen K. We generally use epsilon emissivity instead of K, but right. Assuming the nucleus is at rest, the total energy E of the atom is the sum of the kinetic and potential energies. Okay, so that would be the total energy of the atom. So now we're going to apply Newton's second law, where the electric force of attraction on the electron must equal the centripetal acceleration of the electron. Now, that's just because it's uniform circular motion. Okay, we do the same for a satellite. Okay, all right. So we're kind of setting up the stage of how we're going to relate things. We've got the total energy of the atom. We've got the potential energy of the electron. And then we have a way of talking about relating velocity of the electron in its uniform circular motion to the radius. So we can bring everything together. So let's start doing that. Okay, so we're going to multiply both sides of the equation by r over 2 to get an expression for the kinetic energy, right? So we're going to take the Newton's second law free body diagram of our orbiting electron and change it into a form that looks like kinetic energy so that we can substitute it into the total energy equation. Okay, so now we can use that result to find an expression for the energy of the atom, okay, where the negative value of the energy indicates that the electron is bound to the proton, right? So this is the final total energy of the atom. Again, the nucleus doesn't have any energy other than rest mass, right? It does have E equals mc squared, but it doesn't have any potential or kinetic energy because the nucleus is at rest, okay? And it's at the origin, so it doesn't have any potential. Now, the negative here, I want to just mention it because it's the same negative that we saw for gravitational potential energy. And the reason, and also, I mean, the same negative that we saw when we took, an electron and a proton. And the reason it's negative is because we set zero potential energy at a distance of infinity. So if an atom loses an electron, that electron that's ionized, because it's gone out of the atom, now has zero potential energy because it's so far away from the atom, it's lost contact with it. That's our 0 point. That's where we choose to set the zero because every potential energy system has a choice of where your zero is, okay? But when we choose to set that at 0, that means that all bound energies of the electron, all the ones where the electron is actually in orbit around the nucleus, well, those have to be negative. So again, you can think of it as a potential energy well, right? Because the electron is trapped in orbit around the nucleus. It's in a well. If you pump a bunch of energy into that atom, you can give the electron so much energy that it jumps out of the well and is gone, never to return. If you give it a certain amount of energy, then it goes up the side of the well, but eventually will slide back down to the bottom of the well, okay? And the bottom of the well, to use a term that we'll be using quite a bit, is called the ground state. Okay, so now we're going to make a substitution into our equation for the quantization that came from the de Broglie wavelength idea. So that's the one that I also mentioned in the background. That's quantizing the angular momentum, but ends up also being a fixed number of wavelengths. Okay, and so when we do that, then we can solve for the velocity of an electron at a particular radius. And again, we'll get some numerical practice with this next week. And we can also solve for the radius itself. And so this is the nth radius, this is the nth radius, so we could put an n of 1 for the ground state and n of 2 or so on. And so these are the radii of a bound electron for a hydrogen atom, okay? And n can be any integer. As n grows, the radius grows as well, okay? So again, we got to this result through Newton's classical laws of forces and a classical understanding of conservation of energy. The only thing that would have been modern physics is the idea of only allowing for a fixed number of wavelengths, right? So it's like just a dash of modern physics, okay? But it turns out that a dash of modern physics can give you a good result, okay? At least for, a reasonable model that works for some things, works well for hydrogen. Okay. So the orbit of the smallest radius, called the Bohr radius, we call A naught, and that just corresponds to an n of 0. It's just nice to have this value because we can then kind of factor it out and write simpler equations because there's a lot of variables in here, right? We have here something called h bar, which is just Planck's constant divided by 2 pi. Yeah, divided by 2 pi. And it just kind of simplifies things so we don't have to have as many pi. That way we don't have to have any pi's. We certainly have pi squareds and make the equation look even uglier. But a lot of times we can just factor out the Bohr radius. So it's represented as its own variable. And here's the way then things get really nice. So then we clearly see that each nth radius larger than the ground state, the Bohr radius, is just going to be a square multiple larger, right? So the second radius is 4 times larger than the Bohr radius. The third energy state and its radius is 9 times larger, because 3 squared, than the ground state Bohr radius. All right? Okay. So let's talk some more details about the Bohr model. So then if we want to, okay, so we want to find energy, right? So here is an expression for the energies of the quantum states. If we substitute numerical values, we get this result right here, right? So we get here, right? So if we plug in the particular mass of the electron, if we plug in the electrostatic constant, if we plug in the fundamental charge of the electron, raise them to their appropriate powers, divide by Planck's constant over 2 pi, square it, so h bar squared, with that whole business there ends up becoming 13.6 times 10 to the negative 19 joules, or 13.6 electron volts. Okay, so all we've done here is get rid of all the constants that are specific to electrons and our universe, like the Planck constant, and now we have the energy states of the hydrogen atom. Okay, so this is a great result. It's kind of a good one to remember. It tells you that when you have an n of 1, that's your ground state. That's negative 13.6 electron volts. Again, it's negative because that's the most hold that the hydrogen nucleus can have on its one electron. It can hold on to it with 13.6 electron volts of energy. Okay? And if you put in 13.6 electron volts of energy from an outside source, that would be enough to send that electron out of its well, its potential energy well, and send it off. Okay? Okay. So the figure shows the energy level diagram with the energies of these stationary states and the corresponding quantum numbers. The uppermost level, corresponding to E equals 0 at n of infinity, represents the state for which the electron is completely removed from the atom. Okay, that's called ionization. In this state, the electron's kinetic energy and potential energy are both 0, which means that the electron is at rest infinitely far away from the proton. That's very, very similar to the energy that would be found for the escape velocity of a satellite, right? So if I wanted to give it a satellite on Earth, or a space probe on Earth, just enough kinetic energy so that it left Earth's gravitational pull, the final total energy of that probe would be 0, right? Because it would have coasted away and eventually be infinitely far away at rest. Okay? That's just enough energy. Okay? All right. So we can see our ground state. Here is the second energy state, E of 2, right, and so on. All right? And so you can see then, right, so E of 2 would be a bound energy of 3.4 electron volts. So we represent the total energy of the atom as negative 3.4 electron volts, and so on, right? We can see then that the third energy state would be negative 1.5. They become more close together. Of course they do, okay? So what's happening, because again, this is just solving for the energy, right? And we got this result from the same place that we got everything else, except instead of solving for the radius, we just solve for the energy, okay? But in terms of the constants and the integer. So the energies end up becoming more and more closely packed together as the radii become further and further apart, right? So the radii end up spreading out. So the picture of the radii is like this, right? Where the spacing becomes larger as n gets bigger, but then the spacing of the energies becomes densely packed as n gets bigger. So a good thing to remember, there's an inverse relationship there, okay? And they're both, the spacing is both related to either n squared or inverse n squared, okay? And then let's see, here we can clear up the question I couldn't quite remember. So the Lyman series is everything going down to 1. So yeah, M of 1 is the Lyman series. I knew it wasn't M of 2. The Balmer series is everything going to the second state. So that's an M of 2. So if you use the Rydberg equation, an M of 1 corresponds to the Lyman series. So that's M of 1. And that was from the equation from the previous slide. A M of 2 corresponds to the Balmer. That's the first one that was discovered. And then M of 3 for the Paschen. Right? And then n could be anything. It could be any higher number, because the series has really they're all infinite series. But in practicality, the really high ends don't quite work, because you can see it'd be difficult to raise something to the 64th level, because you probably just want to ionize it rather than get it to that exact value. Because you think energetically the difference between the 64th energy level and the 63rd is minuscule. Okay, all right, which means they'd effectively have the same wavelength anyway when they drop back down to whatever energy state it was, either 1, 2, or 3. Okay, and so this is getting on, this is the very idea of where the frequencies come from, all right? So check it out, right? This is a formula that looks a lot like the Rydberg equation, right? So, which I was just talking about, so good segue. But here, instead of it just being an empirical constant, R sub E, we actually have it based on the assumptions of the Bohr model. Well, it turns out that that's what the Rydberg constant is. The Rydberg constant turns out to be directly predicted by the Bohr model. So the Bohr model must have been a very popular model in 1950, because it ended up explaining something that had been left unexplained for 30 years, right, or 1913. And so, we have this empirical constant that now comes directly from this model, which uses some ideas of quantum mechanics, the idea of the Broglie wavelengths fitting in there, and which, of course, as I said, was based on the quantization of angular momentum. Okay, so this is good stuff. This is real progress. But again, remember that it turns out the Bohr model had some fundamental flaws. Still worthy of a Nobel Prize, and a Nobel Prize was awarded to Niels Bohr for this very model. Okay? So here we have this idea of the different frequencies that are emitted and how to relate those to the quantities of the atom. Okay, and those would be the emission. And here, this is these are really representing emission frequencies. You could do the same thing for absorption frequencies. You would just have to think about that your n final and your n initial would be swapped. Okay. Okay, so good term to mention, the idea of correspondence. So it turned out that the Bohr model had correspondence with classical physics. Okay, so the correspondence principle says that quantum mechanics is in agreement with classical physics when the energy difference between quantized levels are very small. Okay, so we're not contradicting classical physics. We're just saying that these were things that were overlooked by classical physics because they were just immeasurable. They didn't show up. Now, that idea of correspondence is mentioned here. I haven't mentioned it before, but it applies equally well to Einstein's theory of special relativity. That one also has correspondence. We even showed, with relativistic kinetic energy that it simplifies to classical kinetic energy when V is very small. Obviously, so do the relative velocity equations of special relativity, right? All those equations from special relativity, they all simplify. That's the beauty of the Lorentz coefficient, right? Or the Lorentz factor, is that it mathematically is perfect to simplify to classical physics when V is small. Okay, so that's the idea of correspondence, where you have laws of classical physics that aren't being disproven. They just weren't refined enough to notice things. Okay. So the last thing, I think this is the last thing. Yes, the last thing that we'll mention is the hydrogen-like atoms. So it turns out that we can apply the analysis using the Bohr model to hydrogen-like atoms. This is an atom that only contains one electron, but can have multiple protons. This could be like singly ionized helium, doubly ionized lithium, or even triply ionized beryllium. Okay, and you could even imagine something that is even a heavier element like sodium or something, where all but one electron have somehow been ionized away. And in these hydrogen-like atoms, it turns out that it's simply you can do a really simple or addition to the model by just including Z, where Z is the number of protons. That way, if we plug in a Z of 1, we get right back to the Bohr model for the hydrogen atom. But for helium, we'd plug in a Z of 2, and then that would change all of the energy levels rather significantly. So now our ground state for the helium atom would be how many times larger in magnitude than the ground state of the hydrogen. So for how many, the ground state energy of the helium atom would be how many times larger in magnitude than the ground state energy of the hydrogen atom? Well, 4 times larger, because we plug in a Z of 2, we'd be multiplying by 4. Okay, so instead of a ground state energy of 13.6, it's going to be 26 times 2, so 52, right? So about 52 electron volts. And of course, it's a negative energy because it's a bound energy, so negative 52 electron volts approximately for the ground state of the helium atom. Okay, so this also works really well, but they have to only have that single electron, because as we start having more electrons, it turns out things become significantly more complicated. Now, we'll talk later when we talk about X-rays in the third and final video that there's also kind of a special case when you can have more electrons, but you're only worried about the ones in the closest orbits. So more on that later, okay? But this would be an extension of the Bohr model that works quite well, okay? So I'll finish off this video by saying that Bohr's theory was extended in an ad hoc manner, so that's kind of using what works, to include further details of atomic spectra. As these modifications were replaced with the theory of quantum mechanics developed independently by Heisenberg and Schrödinger, we end up getting to kind of this state of Bohr model with more quantum mechanical ideas. And that's going to be covered in the next video. So thank you very much for watching, and I'll see you in the next video.